Hello everyone and welcome to our last lesson in Thermodynamics 1. In this video, we will be discussing the thermodynamics of reacting systems. So this is just a rather short lesson because we have already encountered the energy balance of reacting systems in your chemical engineering calculations class. But specifically in this lesson, we will be discussing how do we determine the absolute enthalpy values of streams that are not at the standard state. Let's begin. Now, before we can have a discussion on the absolute enthalpies of streams that are outside of the thermodynamic standard state, we first have to establish what is our quote-unquote standard state. Specifically, we are talking of the standard thermodynamic state. We define this as an arbitrary set of properties that serve as a reference for calculating state functions for a substance. Those are your internal energy, enthalpy, entropy, and other values. If we use water as our example, we have our steam tables that tells us the value of internal energy, specific volume, enthalpy, entropy for different temperatures and pressures. However, the values of enthalpy found on those steam tables are not absolute enthalpy values. Instead, they are actually values of delta H. Those are H minus H naught, where H naught is the enthalpy at the reference state. That means that those enthalpy values are actually determined against a reference value or a reference state because we cannot directly measure the absolute enthalpy H. Okay? What we can measure is actually delta H. And for that delta H, we need to assign a value for the standard enthalpy for us to determine the actual value of the enthalpy for that state. So for our purposes, we define our standard thermodynamic state as a temperature of 25 degrees Celsius or 298.15 kelvins and a pressure of 1 bar or 100 kilopascals. Throughout our lesson and our examples, we will be using this standard thermodynamic state. The standard state also specifies the phase and form of a substance at the reference temperature and pressure. This is important when we are dealing with the standard state of pure elements because of a definition I will state later. But for now, let's have an example. Water at its standard state is liquid at 25 degrees Celsius and 1 bar. I have mentioned earlier that 25 degrees Celsius and 1 bar are our standard thermodynamic states, and at these conditions, water is at the liquid state. Okay? The liquid phase is its most stable phase at these conditions. Therefore, the standard state of water, to be exact, is 25 degrees Celsius, 1 bar, and in the liquid phase. Okay? Those are very important information for us to specify for the standard state of a substance. Now, water is a compound. Let's examine what are the standard states of pure elements. We have another example here. Oxygen at its standard state is gaseous and diatomic at 1 bar. For gases, it is often just needed to specify the standard pressure or the standard reference pressure that is 1 bar, and we have to consider what is the most stable form of that element at 1 bar. For oxygen, the most stable form is in the gas phase and its diatomic form O2 because the monoatomic form O is unstable and it reacts readily with other substances. So the most stable form of oxygen is actually O2. Now, there are other allotropes of oxygen such as ozone, which is O3, but that is not the most stable form of oxygen at a pressure of 1 bar. Ozone is very reactive and it can also self-degrade. So you have to remember which elements are stable in their diatomic form. We actually have 7 common elements that are naturally and are stable in the diatomic form. We have a mnemonic that is have no fear on ice cold beer. Those stand for hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Those are 7. Have no fear on ice cold beer. Okay? Those are flashed in your screen right now, and remember that they are stable in their diatomic form. But take note that 5 of them are gases, 1 is a liquid, and the other is a solid. Okay? Another example here is carbon. At its standard state is solid and of the graphitic form or its graphite at 25 degrees Celsius and 1 bar. As we all know, carbon has several allotropes. That is carbon in the form of graphite, carbon in the form of diamond, carbon in the form of buckyballs, etc., etc. Therefore, we are saying that carbon in the graphite form, solid, is the most stable at the standard state of 25 degrees Celsius and 1 bar. Okay? That is how we define the standard thermodynamic states of substances. Now, let us focus on the standard thermodynamic state of elements or pure elements. Let's start with this definition. A pure element at its standard state is defined to have a reference standard enthalpy of formation of 0. Take note of the term standard enthalpy of formation. For a pure element, at its standard state, the enthalpy of formation is 0. For example, oxygen gas that is diatomic at 25 degrees Celsius and 1 bar has an enthalpy of formation of 0. This definition or this statement has wide-ranging implications in the study of reaction thermodynamics because everything will be based from this enthalpy of formation values. Okay? As you all know, elements can form compounds, and we can determine the enthalpy of formation of compounds coming from this definition of the enthalpy of formation of the elements. How do we do that? Consider the following reaction: hydrogen gas plus 1/2 oxygen gas yields H2O gas. As you will notice, hydrogen is in its standard phase, that is gaseous and diatomic. Oxygen is also at its standard phase, gaseous and diatomic, and water is in the gas state. We have two elements and we have one compound. For this specific reaction, we can represent it as a steady flow process in a reactor. So imagine that we have this reactor and we have incoming 1 mole of hydrogen, 0.5 mole of oxygen, and 1 mole of water as the output. Now, for this to become a steady-state reactor, let us assume that all of these values are for a basis of 1 second. So we have a flow rate of 1 mole per second hydrogen, 0.5 mole per second oxygen, and an output of 1 mole per second of water. For this process, let us examine the first law of thermodynamics equation, which we have been examining for the entire term by now. We have here our unsteady state term, our derivative with respect to time. We have here our flow stream terms, enthalpy, kinetic energy, and potential energy. And we also have here the heat transfer term and the shaft work term. If we assume that the process is steady state, then we cancel our derivative with respect to time. And if we assume that kinetic and potential energies are negligible, as well as there is no shaft work involved in this process because it's just a simple reactor, then we will end up with this equation here. We have the heat transfer. We have the rate of heat transfer Q is equal to the molar flow rate of water multiplied by the enthalpy of water, because this is your output. Remember, delta here is output minus input. Output minus inputs. For the input, we have two terms because we have two separate reactants. If you will notice, I have switched out the mass flow rate M with the molar flow rate N. Okay, we can do this by assuming that our specific enthalpy term here is a molar enthalpy term. This equation further simplifies to this one, that is the rate of heat transfer is equal to the enthalpy of the products minus the enthalpy of the reactants. Or if we subtract this, we call this delta H reaction, or the enthalpy of the reaction. From now on, we will take a look at delta H reaction as a difference between the total enthalpy of the products minus the total enthalpy of the reactants. Now, let us consider what happens if we are under standard conditions. That is, we are at 25 degrees Celsius and 1 bar. We can write our derived equation in terms of the standard enthalpy values. We have the standard enthalpy of reaction is equal to the standard enthalpy of water minus the standard enthalpy of hydrogen plus the standard enthalpy of oxygen. As we have mentioned earlier, the standard enthalpy of the pure elements at the standard state is equal to their standard enthalpy of formation, and the standard enthalpy of formation is 0 for pure elements at their standard state. Therefore, our standard enthalpy of reaction is equal to our standard enthalpy of water, which is now determined as the standard enthalpy change of formation of water. Okay? This value is a constant, the standard enthalpy of formation of water. We can find values of these constants in the appendices of our thermodynamic books. And this will serve as our reference value for our determination of the enthalpies outside of the standard state. Since this is our conclusion, we can say that our previous reaction, hydrogen gas plus 1/2 oxygen gas yields water gas, is a standard molar enthalpy of formation reaction. What makes a reaction a standard molar enthalpy of formation reaction? We have three criteria. The first and the most important criteria is all of your reactants must be elements at their standard state. If you take a look at hydrogen gas, this is at its standard state. It is diatomic and it is gaseous. For oxygen, that's the same. It is diatomic and it is gaseous. That's the first criteria. The second criteria is you should only have one product, and our product is water gaseous. Another subset of that condition is that your product must be a compound. Of course, when you are combining two or more elements and you're only allowed to have one product, that product must be a compound. Okay? And the last criteria or the third criteria is your product must have a coefficient equal to 1. To repeat, we have our three criteria for a reaction to be a standard molar enthalpy of formation reaction. That is, all of your reactants must be pure elements at their standard states. The second is you should only have one product, which is a compound. And the third is your product must have a coefficient of 1. If all of those three criteria are satisfied, then the standard molar enthalpy of reaction for this standard molar enthalpy of formation reaction is equal to the standard enthalpy of the product. And this is how we determine the values of the standard molar enthalpy of formations of substances by writing them in terms of the standard molar enthalpy of formation reaction. To give you more of an idea, what does that look like? We have here two examples. Take a look at these two thermochemical equations. We have the same thermochemical equations, but they have different values of the standard enthalpy of reaction. The first reaction, we have hydrogen gas plus bromine liquid yields 2HBr gas. Enthalpy of reaction, negative 72.8 kilojoules per mole. Now, why is the first reaction not a standard molar enthalpy of formation reaction? You go back to our three criteria. The first criteria is satisfied because our two reactants are at their standard state. Hydrogen gas, diatomic, bromine liquid, diatomic. For the second criteria, we only have one product, that is HBr, that is satisfied. However, for the third criteria, we need to have our product to have a coefficient of 1. Therefore, the first equation is not a standard molar enthalpy of formation reaction. How do we convert it to 1? We simply divide both sides of the equation with the coefficients 2. We have the following equation. 1/2 hydrogen gas plus 1/2 bromine liquid yields HBr gas. And if we divide the equation by 2, our enthalpy of reaction will also be divided by 2. Therefore, we now have a standard molar enthalpy of reaction because it satisfies our three criteria. And the enthalpy of reaction for this standard molar enthalpy of formation reaction is also equal to the enthalpy or the standard enthalpy of formation of the product, which is HBr. Okay? Therefore, we can say that the standard enthalpy of formation of HBr is equal to negative 36.4 kilojoules per mole. This is a constant value because this is only applicable under standard conditions. That is at 25 degrees Celsius and 1 bar. Okay? And this becomes our reference value for all of the enthalpy calculations for HBr. For other substances, we can simply look at some tables in the appendices of our thermodynamic books and we can have the values for the standard enthalpy of formation for the other substances. Now, let us interpret what value do those standard enthalpy of formation values give us. Well, those values are used to determine the enthalpy of a substance at conditions different from the standard state, as I've mentioned earlier. Let's have this example. The enthalpy of superheated steam at 300 degrees Celsius and 1 megapascal, which is definitely outside of the standard state, is determined as delta H, or the change in enthalpy, is equal to the specific enthalpy at 300 degrees Celsius and 1 megapascal, which is not our standard state, minus the specific enthalpy at our standard state. That's 25 degrees Celsius and 1 bar. We can rearrange this equation for us to determine the standard enthalpy at the given state, 300 degrees Celsius and 1 megapascal, as enthalpy is equal to delta H plus the standard enthalpy of formation. Okay? For this equation, The standard enthalpy of formation is a constant. So we just need to figure out how do we determine the value of delta H. If we can determine delta H, we simply add it to the enthalpy of formation, then we can have the absolute enthalpy at the specified conditions. Now keep in mind that in this slide, I am using small letter h. You have to always keep in mind the differences of the small letter h and the capital letter H for enthalpy. The small letter denotes specific values, while the capital letters denotes an absolute value. Okay? In this case, this equation is true both for the specific enthalpy values and for the absolute enthalpy values. So they are interchangeable in this case. Okay? You can prove that by simply factoring out the mass or the molar term, and they will cancel from both sides of the equation. Now let us discuss how do we determine the value of delta H, because that is important. Let's first visualize the process of converting enthalpies through this diagram. So from the previous example, we have our standard states at 25 degrees Celsius and 1 bar represented by this circle here, and we want to get to the given states, which is 300 degrees Celsius and 1 megapascal. So ideally, we already have the value of the enthalpy of the standard state, that is the enthalpy of formation. We want to determine the enthalpy of the given states, 300 degrees Celsius and 1 megapascal. And we can do that by determining the value of delta H. The red arrow here symbolizes our actual path. It's from the standard state to the given state. The problem is, how do you determine the delta H for this actual path? Now, since enthalpy is a state function, it does not care how many steps do we need to take for us to go from the standard state to the given state. It only cares about the initial and the final state. So for this purpose, let us define an intermediate state. For the intermediate state, you first have to take a look at the standard state, and let's try to change the temperature while the pressure remains constant. So from 25 degrees Celsius, let us increase that to 300 degrees Celsius while the pressure remains at 1 bar. We have change in temperature but a constant pressure. Okay? And finally, from the intermediate state going to the given state, we do the reverse. We change the pressure but we keep the temperature as a constant. So from 1 bar, we increase the pressure to 1 megapascal while the temperature remains at 300 degrees Celsius. So it's a two-step process, but if you take a look at the delta H values, they're still the same because again, enthalpy is a state function. We only care about the initial and the final state. So for us to determine the delta H of the actual path, we just have to determine the total delta H from two contributors. The first is with the changing temperature, constant pressure, and the second is with the changing pressure, constant temperature. Let us find out some of our techniques for those two contributors. Let us first consider constant pressure with a change in temperature. The temperature dependence of enthalpy at constant pressure is delta H is equal to the integral of Cp dt from the bounds T1 to T2. We have three outline cases here. All of this could be applicable, but keep in mind that they have their own limitations. For the first case, we are assuming that Cp is constant. It's either constant or it's assumed to be constant over the temperature range. Therefore, if Cp is constant, we can move it out of the integral and we just have the integral of dt, which is delta t. We have the equation delta H is equal to Cp times delta t, which we are all familiar of. Okay? But you have to be careful with case 1 because if you're assuming that Cp is constant, you have to make sure that over the entire temperature range, the heat capacity value will not vary considerably. For example, if your substance is air and you're integrating from 25 degrees Celsius to 50 degrees Celsius and you are using the constant specific heat at 25 degrees Celsius, that is okay. Because from 25 to 50 degrees Celsius, there is not much difference with the value of heat capacity for air. However, if your integration range is from 25 degrees Celsius to 800 degrees Celsius, that already represents a big error because the heat capacity values of air from those two different temperatures are very different. Okay, so be careful in using case 1. Now from case 1, which is the simplest, let's go to case 2, which is the most difficult or the one that involves the most work, but this is also the most accurate. We are to assume that Cp has a defined temperature function such as the following. Cp is equal to A plus B times T plus C times T squared, wherein small a, b, and c are constants and T is the temperature. If you substitute this definition of Cp into our enthalpy equation, we have delta H is equal to the integral of A plus BT plus CT squared times dt from T1 to T2. Now, this is still manageable because the integral of this expression is relatively easy. And you can also do this directly in the calculator because you are given the boundaries from T1 to T2. However, if you are treating many substances in a single stream, let's say for example for air, in which we are assuming to have three substances, nitrogen, oxygen, and argon, you have to do this 3 times for the 3 components. So there is a lot of work involved for the case 2. However, this is the most precise because we are incorporating the changes in heat capacity with respect to the change in temperature. Now, as a compromise between case 1 and case 2, we have case 3. In case 3, we are assuming that the heat capacity averaging is acceptable such that we define a heat capacity value average that is equal to Cp at temperature T1 plus Cp at a temperature T2 divided by 2. And this Cp average is a constant, so this can be brought out of the integral. So we have delta H is equal to the average heat capacity multiplied by delta T. Case 3 combines the simplicity of case 1 and the accuracy of case 2. So in most cases, we can use this expression. However, as with all assumptions, there are limitations. You cannot use case 3 if the heat capacity function over the entire temperature range you are studying is not a linear function or does not approximate a linear function. If it is a strong quadratic function, meaning it's not a straight line, then the averaging of the heat capacity will not be suitable for that substance. Okay, we have to resort to case 2. Next, let us discuss how do we determine the enthalpy change for constant temperature and changing pressure. Now, this is a little bit uncommon because throughout our lessons, we have been assuming that the enthalpy change of gases are independent of pressure. Now, that statement is partly true as we will discuss later. The pressure dependence of enthalpy at constant temperature is given by this relationship. The change in enthalpy with respect to pressure at constant temperature is equal to negative temperature times the change in volume with respect to temperature at a constant pressure plus the volume. For most substances, the change in volume with change in temperature at a constant pressure, or this term here, is defined in the coefficient of expansion alpha. Alpha is equal to 1 over V times the change in volume with respect to temperature at a constant pressure. If we substitute this relationship back into our previous equation, we will have this final equation. That's the change in enthalpy is equal to the integral of V times 1 minus alpha T times dP from P1 to P2. This expression looks familiar, especially if we are determining the enthalpy change of a pump. That is simply V dP, and if we are assuming that V is constant, then we have V delta P. For this expression, let us examine what happens if we consider different substances. First, for ideal gases, this is automatically zero at constant temperature regardless of pressure. That is why for most of our applications, we have been neglecting the contribution of the change in pressure in the enthalpy of ideal gases, because this equation mathematically reduces to zero for ideal gases only. For real gases, you need to evaluate the change in volume with respect to temperature at constant pressure using equations of state. So let's say, for example, we have the Peng-Robinson equation or the Suave-Redlich-Kwong equation. You simply need to get the derivative of volume with respect to temperature at constant pressure. Once you get that expression, you substitute it here and you solve for delta H. That sounds very tedious for real gases, but for most cases, you would find out that the value of delta H for changing pressure is very small compared to the value of delta H for changing temperature. Okay, so most of the time we are neglecting it. For solids and liquids, we can often assume that the volume is independent of pressure, or that is an incompressible substance. That means that our volume gets taken out of the integral. So when you integrate this simply becomes volume times 1 minus alpha T times delta P. For substances with very, very low values of the linear expansion coefficient, the term alpha T becomes a very small value such that 1 minus alpha T is almost equal to 1. So this equation simply reduces to volume times delta P, which is the equation that we have been using to determine the enthalpy change of compressed liquid water in a pump. Keep in mind that this simplification is only applicable for incompressible liquids and solids. Now, to summarize, we simply combine the contributions of temperature and pressure on delta H. For instance, for a real gas, our delta H total is equal to the contribution of temperature, that is your Cp function dt, integrate from T1 to T2, plus your change in enthalpy due to the change in pressure, dP, from P1 to P2. So as you can see, this is a very complicated equation and it is very tedious to evaluate for each and every substance. If you have 5 substances in your reaction, then you have to do this 5 times. If that sounds like a lot of work, good news for you, because alternatively, we can use generalized charts for enthalpy change. So no need to evaluate these equations, we can simply consult a chart. We call that the Lee-Kessler simple fluid enthalpy departure chart. There are other types of charts besides the Lee-Kessler chart, but for the purposes of our discussion, I will be using this chart because this is relatively simple to use. This chart simply needs the reduced temperature and pressure of the substance. The reduced temperature is the ratio between the actual temperature and the critical temperature of the substance, and that is also true for the reduced pressure. And coming from this chart, it gives us the value of delta H for the different fluid phases of a substance. So we can consider both liquid and gaseous states. We have here the saturated liquid line. We have here the saturated vapor or saturated gas line. And at the middle here, at a reduced pressure of 1, and at a reduced temperature of 1, this is the critical points of your substance. Let's try to solve this example. A combustion chamber receives 10 mole per second of methane along with 20% excess air, all at atmospheric pressure. The combustion products exit at 800 degrees Celsius and 1.5 bar. Determine the heat released by the combustion chamber. Here we have our given for the problem. So I have represented the combustion chamber as a reactor. We have the feed, that's 10 moles per second of methane, along with 20% excess air. And it was specified that our feed and the air are at 25 degrees Celsius and 1 bar, while our flue gases exit at 800 degrees Celsius and 1.5 bar. Before we can solve this problem, we have to acknowledge one basic assumption. And we are assuming that the process undergoes complete combustion, because there was nothing stated in the problem about the composition of the flue gas or the amounts of the flue gas. The only way we can solve this problem is if we assume complete combustion. As such, our governing chemical equation is methane plus oxygen yields carbon dioxide plus water. This is our basic combustion reaction. Balancing, we simply multiply water by 2 as well as oxygen. It's important to have this balanced equation because this is the basis of our percent excess of the air. Now, to start with the solution, let's first have the material balance before we can proceed with the energy balance or the first law of thermodynamics. Okay? For that, we specify our basis, that is 1 second operation, because our feed is given as a molar flow rate. So that gives us a feed of 10 moles of methane. Now, let's solve for NO2 Theo, or the theoretical amount of oxygen that is consumed in this process. We need this value because we are given the percent excess of air. How do we solve that? That's simply 10 moles of methane, that is from our feed, and we perform stoichiometry using our balanced combustion equation. That is, for every 1 mole of methane, there are 2 moles of oxygen consumed. Therefore, our NO2 Theo is 20 moles oxygen. This theoretical amount of oxygen can be used with the definition of percent excess air. The percent excess air is numerically equal to the percent excess oxygen. That is simply NO2 fed minus NO2 Theo over NO2 Theo. Since we have a value of 20%, we can solve for the value of NO2 fed. This NO2 fed is our oxygen in the air. And once we get this, we can also get the amount of nitrogen coming from our air. Okay? Solving, we have 20% or 0.2 multiplied by our NO2 Theo, 20 moles, plus the theoretical amount, 20 moles. Our NO2 fed is 24 moles O2. We can now say that our input air contains 24 moles of oxygen. How do we determine how much nitrogen is in our input air? We simply multiply this ratio by the percent composition of air. we are assuming that air contains 21% oxygen and 79% nitrogen. And from this ratio, we simply multiply 24 by 79 and divide it by 21. We have here the amount of nitrogen in the air. That is 90.29 moles nitrogen. So we're done with the air. Now we can focus on the flue gas. Now, since we have assumed that our process undergoes complete combustion, the only substances in your flue gas would be carbon dioxide and water, which are your products, plus the excess oxygen and excess nitrogen from your air. Keep in mind that as long as we have percent excess from the air, you will have excess oxygen and nitrogen in the flue gas. This is a common composition of flue gases for material balance calculations involving combustion. Okay? Let us denote this as N1, N2, N3, and N4 to facilitate an easy solving of their values. Let us start with N4, or for the nitrogen in the flue gas. Nitrogen here is considered as an inert unless it's specified that nitrogen reacts to form NO2 and other nitric oxides. If it's not specified, then we are to assume that it is inert. Therefore, we say that N4 is also equal to 90.29 moles of nitrogen. Okay? For N1, N2, and N3, we can perform atomic balances or elemental balances to determine their values. Let's start with a carbon balance. For the carbon balance, we have an input, which is 10 moles of carbon in the feed, is equal to N1 moles of carbon in the product. Therefore, we have N1 is equal to 10 moles of CO2. Next, we perform the hydrogen balance. In the reactants, there are 4 moles of hydrogen coming from methane. So that is 4 times 10. And in the product, only water contains hydrogen. So that is 2 times N2, representing the 2 moles of hydrogen in water. Solving, N2 is equal to 20 moles H2O. And finally, we have the oxygen balance. Coming from the fuel, there's no oxygen, but coming from the air, there are 2 moles of oxygen. So that's 2 times 24. And in the product, that's 2 N1 plus N2 plus 2 N3. This represents all of the oxygen coming from the flue gas. So there are 2 moles from CO2, 1 mole from water, and 2 moles from O2. We have the values of N1 and N2, so we can directly solve for N3. Solving, that is 2 times 24. We subtract 2 times N1. N1 is 10. And we also subtract N2. That's 20. And we divide this by 2. Our oxygen in the product is 4 moles O2. So what's important here is we now have finished the material balance and we have determined the amount of moles of all of your substances in the reactant and in the product. Our reactant streams are both the fuel, F, and the air, which consists of methane, inlet oxygen, and inlet nitrogen. While our product stream contains 4 components, that is carbon dioxide, water, excess oxygen, and excess nitrogen. Now, to facilitate our first law of thermodynamics expression, this can be written as the summation of the output enthalpy or the enthalpy of the products minus the summation of the enthalpy of the reactants is equal to Q, or the rate of heat transfer. In this case, we are assuming that there is no shaft work involved. The kinetic and potential energy contributions are negligible compared to the enthalpy contributions. So for us to solve for the rate of heat transfer, we simply have to solve for the absolute enthalpies of the products and subtract from that the absolute enthalpies of the reactants. This is where our scale of determining the values of absolute enthalpy come into play. For that, I have constructed this table here. This table has already summarized our input and output substances. We have several rows here representing both the material and energy balance. The material balance is represented by the number of moles of the substances. From our previous calculation, we have determined that for methane input, we have 10 moles. Oxygen input, we have 24 moles. Nitrogen input, we have 90.29 moles. And that is also the amount of nitrogen output. So that's still 90.29 moles. For the output carbon dioxide, we have 10 moles. Output water, we have 20 moles. And excess output oxygen, we have 4 moles. Okay, we will return to those molar values of the substances later. In the third column, you see that I have already listed the enthalpy of formation values of those substances. The enthalpy of formation values, as I've mentioned, are constant because they are measured at the standard states of 25 degrees Celsius and 1 bar. For the book Fundamentals of Thermodynamics by Borgnake and Sontag, this is listed in table A.10. This is the table that we are pertaining to, table A.10. In here, you can see several commonly used substances and their values of the standard enthalpy of formation and the standard entropy of formation. The units of the standard enthalpy of formation are in kilojoules per kilomole or in joules per mole. I have listed the values of methane, CH4, that's negative 74,873. Carbon dioxide, that is negative 393,522. And finally, for water. Now, take note that for water, there are two entries. One for the gaseous water or vapor water, and one for liquid water. In our case, for combustion, we are considering the vapor or the gaseous water, negative 241,826. Take note that they have different values, so please be careful in determining the standard enthalpy of formation of water for the two different phases. Okay, let's go back. It is also important to take note here that there are enthalpy of values that are zero for some substances, and those are for the pure elements in their standard form. So diatomic oxygen gas, 0. Diatomic nitrogen gas is also 0. That is applicable for both the input and the output. Now you might be asking, the input is at the standard state of 25 degrees Celsius and 1 bar, but our output is at 800 degrees Celsius and 1.5 bar. Why did I list that the enthalpy of formation values are still at the standard states? Well, we have listed these values for the purpose of determining the actual enthalpy. Okay? So regardless of the state of the output, even though it's not at the standard state, the value of the enthalpy of formation of the substances at standard state is still constant. We just have to add our delta H to those substances. Now, for the next few columns, we will be estimating the values of the enthalpy change, delta H, for a changing temperature and for a changing pressure. And if we add those, we get the total delta H, just as what we have discussed earlier. We will be trying our first method, and that is to assume that everything behaves ideally. So all of them are ideal gases. For our input substances, all of our delta H are 0 without question. Why? Because our input is at 25 degrees Celsius and 1 bar. These are your standard state. Therefore, your H or your final enthalpy is still equal to the standard enthalpy of formation for those substances. So this is negative 74873 for methane, still 0 for oxygen and nitrogen. Okay, take note of the formula above for the final enthalpy, and that is the standard enthalpy of formation value plus delta H. Our delta H total is 0 if your substances are on the standard state. Let's move on to the outputs or the products. On our final column, we have our capital H or our final absolute enthalpy. This is obtained by simply multiplying the specific enthalpy H with the number of moles that we have earlier determined from the material balance. Okay, multiplying, this becomes negative 748,730. It's still 0 for oxygen and nitrogen. We have a subtotal for the reactants of negative 748,730. This is in joules. Now let's move on to the products or the output. We will have a different treatment for the output substances because these are at 800 degrees Celsius and 1.5 bar. So if you will compare this with our initial state or our input state, both the temperature and pressure varied. However, since we are assuming that these are ideal gases, and as we have determined earlier, the change in enthalpy for an ideal gas with regards to the change in pressure at constant temperature is equal to 0. Therefore, the delta H change with respect to pressure is 0 for all of these outputs. Always remember that for the ideal gas assumption. The only thing that will have a value here is our delta H coming from the change in temperature. And we can determine that using several methods as we have discussed earlier. The first method, or case 1, is to assume that their heat capacity is constant, which we will not do because from 25 degrees Celsius to 800 degrees Celsius, that is a very big temperature change and we cannot assume a constant heat capacity. So we have two choices. Either we perform case 2, in which the heat capacity is modeled as a function of temperature, or we can do case 3, wherein we can get the heat capacity of the gases both at 25 and 800 degrees Celsius and then average it to get our delta H with respect to temperature. Okay? But lucky for us, there are tables dedicated for combustion products which already give us the value of delta H with respect to temperature change for ideal gases. If we go back to our thermodynamics book, from table A.9, we have the ideal gas properties of various substances. These are at 0.1 megapascal and mole basis. Let's first take a look at this. Let's first take a look at nitrogen. In here, we have nitrogen diatomic with a standard enthalpy of formation of 0 kilojoules per kilomole. That means that it's an element at its standard state. If we consider this column here, we have H minus H naught. This represents your delta H with respect to temperature, meaning we only need to determine the temperature of your outputs and then locate your temperature. If it's not directly listed here, we simply have to interpolate and we already have the value of the delta H. These delta H values are determined by integrating the heat capacity function of temperature with respect to temperature. So instead of us integrating long equations, we can simply take a look at this table and we already have the values. Okay, these are for ideal gases. So let's begin with nitrogen. Our output temperature is 800 degrees Celsius. Converting to Kelvin, that is 1073.15 Kelvin. So that is between 1000 and 1100 Kelvin. Upon interpolating, we have our delta H value of 23,875 joules per mole. And we will be doing the same for all of the substances in our output. So we are finished with nitrogen. Let's go to the next table. This is for oxygen diatomic. Let us interpolate between 22703 and 26212. We have a value of 25,270. Let's take a look at the other entries for this table. We have carbon dioxide, which is another one of our combustion products. Interpolating between 33397 and 38885, we have a value of 37,411. These are all in joules per mole. Okay? And finally, we need the one for water vapor. Okay, this is water vapor. We need to interpolate between 26,000 and 30190. Upon interpolation, the value is 29,065. Let's go back to our board. We now have completed our delta H values with respect to temperature changes. We have earlier determined that our delta H with respect to pressure changes is 0 because we have ideal gases. As such, our delta H total is simply equal to the delta H with respect to the change in temperature. Now let us fill out the second to the last column, that is our actual specific enthalpy. You can see the formula above, that is simply the standard enthalpy of formation of the substance plus the delta H total. Let's calculate. For CO2, that is negative 393,522 plus 37411. We have negative 356,111. These are still in joules per mole, okay? Next, for water, we have negative 241,826, and we add 29065. We have negative 212761. You have to be careful with the signs, whether it's negative or positive, okay? Next, for both oxygen and nitrogen, since their enthalpy of formation is 0, then we have the same value of final enthalpy, 25270 and then 23875. And finally, we can multiply our specific enthalpy with the number of moles of the substances to get the final absolute enthalpy. So for carbon dioxide, that is times 10. This becomes negative 3561110. For water, that is negative 212761 multiplied by 20 moles. That is negative 4255220. We will just be converting to kilojoules later after we're done with all of this, okay? For oxygen, that is 4 moles times 25,270 joules per mole, that is 101080. For nitrogen, that is 90.29 times 23,875. That is 2155674. And finally, let us add all of the enthalpy terms in the outputs. So we have here the 1 for nitrogen. We add 101080 for oxygen plus negative 4255220 for water vapor plus negative 3561110 for CO2. Our total, negative 5559576. This is in joules. At this point, we have finished our determination of the enthalpy because we were able to get the summation of the enthalpies of the reactants and the summation of the enthalpies of the products. If you go back to our simplification of the energy balance, that is, the rate of heat transfer is equal to the summation of the enthalpy of the products minus the summation of the enthalpy of the reactants, we can actually now solve this to determine the rate of heat transfer from the reactor. That is negative 5559576 minus negative 748,730. These are all in joules. Converting this to kilojoules by dividing by 1,000, we have negative 4,811 kilojoules. But since our initial basis was for 1 second of operation, we can have this as kilojoules per second. This is now our rate of heat transfer from the reactor. Okay? And that is the general flow of solution for incorporating chemical reactions to our usual energy balance using the first law of thermodynamics. For an orderly solution, I would encourage you to follow the same format of the table whenever we are dealing with such problems. Okay? This format of the table allows us to specify the values both from the material balance in the form of the number of moles and the energy balance in the form of the enthalpy departures. We can also specify the contributions to delta H coming from the change in temperature and from the change in pressure. For the flow of solution involving real gases or for the other methods of estimating the value of delta H, I'll be showing that in a separate video under a different solution. Okay? But for most purposes, this flow of solution involving the assumption that our substances are ideal gases is satisfactory. What's important for you to understand is the process on how we determine the actual absolute enthalpy of each of the substances and how we add them up in order for them to be incorporated in our first law of thermodynamics analysis. Okay? Please do watch out for other videos detailing specific examples and specific applications of this first law analysis for reacting systems. This involves more systems on combustion, particularly determining the adiabatic flame temperature, as well as its application in liquid phase reactions. That's it for this video. I hope you have learned something. Thank you for listening, and as always, keep safe.